Alright, hi Year 11s, this is Mr. Lim here, and today we're going to be doing a video about rates of reaction and what happens when you change the temperature. So let's have a look. Okay, so this is what we're going to be learning about. We're going to be learning about changes in temperature, alright, and so what we're going to be able to describe what a change in temperature is, describe how changes in temperature affect the particles in terms of the collision theory, okay, so collision theory, very important. Predict what happens to the rate of reaction when you change the temperature, and then draw changes to temperature in energy distribution graphs, and then be able to use that as an explanation. Okay, so let's get going. All right, so what is the change in temperature? Temperature is the average kinetic energy of the particles that making up the substance. So it's the average kinetic energy. Okay, and so you might have seen, we've probably talked about this before in an energy distribution graph. It is the peak of the curve. So what does that look like? Here is your energy distribution graph, right? This is the peak of the curve, so this is the temperature, okay? Or for all intents and purposes, the temperature is representative of that peak, okay? So ideally, you should remember that temperature should not be, or should not be thought about in degrees Celsius, but in Kelvin, okay? And so Kelvin is what? It's degrees Celsius plus 273.15, okay? So therefore, 10 degrees Celsius is not half of 20 degrees Celsius. It's like it's quite close to it in terms of value, actually. All right, the greater the average kinetic energy, the greater the temperature. So you're going to see me discuss the word proportional relationship lots. Okay, the idea is that you wouldn't actually use the words proportional relationship in a answer. You should be just talking about, okay, when you increase the temperature, you increase the average kinetic energy, or when you decrease the temperature, you decrease the average kinetic energy. You just understand that that's a proportional relationship, and it's just an easy way of me to say it, rather than saying when it goes up, it goes up, it goes down, it goes down. Okay, so let's move on. Describe how changes to the temperature affect the particles in terms of collision theory. Okay, so if you think about it, right? If the particles are moving faster in the same sized container, okay, so in 1 second it might go this far, and when it's at 15 degrees, okay, but if it's at 400 degrees, it's going to go much further in the same amount of time. And if it's going to go much further in the same amount of time, it's going to collide more often. Okay, so that is the frequency of collisions increases as the temperature increases. Okay, so the frequency of collisions is the first thing that it changes in terms of the collision theory. And then it also changes the proportion of particles with sufficient energy. Okay, so the higher the temperature, the higher the proportion. Again, that's a proportional relationship. Okay, it's really important to remember to use this word proportion. Okay, so it's about saying what percentage of those particles have sufficient energy to react. Okay, so that's how it affects the temperature affects the particles in terms of collision theory. Predict changes to the rate of reaction in terms of changes in temperature. So, well, if this is the temperature and this is the rate of reaction, it's a proportional relationship. So what should you see? Something like this again. Okay, so as the temperature goes up, the rates of reaction goes up. That makes sense. Okay, so draw changes to temperature in energy distribution graphs. Okay, so again, it can be shown in an energy distribution graph by changing the shape of the bell curve. Okay, the shape of the bell curve to show a different temperature. Okay, so we have discussed this before, but we'll go through it over again. And if you are doing it, remember to keep the area underneath the curve, which is how many particles there are effectively, the same unless you are simultaneously changing the concentration. Okay, so how are we going to draw a different shaped bell curve with the same area? Okay, so let's take it into account. Let's say that it gets colder. Okay, if it gets colder, we know that the peak here is going to move towards the left. Okay, and so if the peak moves towards the left, it will look something like this. Start at the bottom, remember? Oops, that's terrible. Okay, so what's happened is that I've gone backwards in that, and you can't go backwards in one of these curves. So I'm just going to get rid of that. Let's do it again. Let's try again. Okay. Okay. So why have I made this peak much higher than that peak? Okay, because remember, we've got to have the same area underneath the entire curve, right? which will mean that I have the same substance effectively. Okay, so that's my initial curve, but for a decrease in temperature. How would I draw it if we were trying to draw an increase in temperature? Well, you would need to make sure that the peak is towards the right. Okay, peak should be lower, and it should, well, as I've said before, it should skew to the right, and that was just a terrible drawing. It should skew to the right, and so that it should be there, and if you need to, you extend the axes. Okay, so the peak to the right, the peak is lower because we need to still have the same area for the two curves. Okay, then we also need to take into account, okay, well, here is the activation energy, the vertical line to show that that's how much energy the particles need. For the blue one, it's only got a very small proportion of particles which have sufficient energy. For the black one, which is the original temperature, we have a larger proportion of particles with sufficient energy. And then for the red one, we have quite a large proportion of particles with sufficient energy. Okay, that's a proportion of the total amount. Okay, so that's how you would draw it. Keep the activation energy in the same place and draw it with different peaks to show that it's at different temperatures, up and higher and lower, and then show the proportion of particles with sufficient energy. Okay, and that's that for changes in temperature.